The sulfur mustards, or sulfur mustards, commonly known as mustard gas, are a class of related cytotoxic and vesicant chemical warfare agents with the ability to form large blisters on the exposed skin and in the lungs. Pure sulfur mustards are colorless, viscous liquids at room temperature. When used in impure form, such as warfare agents, they are usually yellow-brown in color and have an odor resembling mustard plants, garlic, or horseradish, hence the name. Mustard gas was originally assigned the name Lost, after the scientists Wilhelm Lommel and Wilhelm Steinkopf, who developed a method for the large-scale production of mustard gas for the Imperial German Army in 1916. Mustard agents are regulated under the 1993 Chemical Weapons Convention. 3 classes of chemicals are monitored under this convention, with sulfur and nitrogen mustard grouped in Schedule 1, as substances with no use other than in chemical warfare. Mustard agents could be deployed on the battlefield by means of artillery shells, aerial bombs, rockets, or by spraying from warplanes. Synthesis: sulfur mustard is the organic compound with formula 2S. In the Dupret's method, sulfur mustard is synthesized by treating sulfur dichloride with ethylene, SCl2 plus 2C2H4 2S. In the Levenstein process, disulfur dichloride is used instead, 8S2Cl2 plus 16C2H4 82S plus S8. In the Mayer method, thiodiglycol is produced from chloroethanol and potassium sulfide and chlorinated with phosphorus trichloride, 32S plus 2PCl3 or 32S plus 2P, OH, 3. In the Mayer-Clark method, concentrated hydrochloric acid instead of PCl3 is used as the chlorinating agent, HOCH2CH2, 2S plus 2HCl or 2S plus 2 hours 2O, thionyl chloride and phosgene have also been used as chlorinating agents. It is a viscous liquid at normal temperatures. The pure compound has a melting point of 14 AA degrees Celsius and decomposes before boiling at 218 AA degrees Celsius. Mechanism of toxicity: the compound readily eliminates a chloride ion by intramolecular nucleophilic substitution to form a cyclic sulfonium ion. This very reactive intermediate tends to permanently alkylate the guanine nucleotide in DNA strands, which prevents cellular division and generally leads directly to programmed cell death, or, if cell death is not immediate, the damaged DNA may lead to the development of cancer. Oxidative stress would be another pathology involved in sulfur mustard toxicity. Sulfur mustard is not very soluble in water but is very soluble in fat, contributing to its rapid absorption into the skin. In the wider sense, compounds with the structural element BCH2CH2X, where X is any leaving group and B is a Lewis base, are known as mustards. Such compounds can form cyclic anion ions that are good alkylating agents. Examples are bis, 2-chloroethyl, ether, thymines, and sulfur sesquimustard, which has 2I plus or minus chloroethyl thioether groups connected by an ethylene group. These compounds have a similar ability to alkylate DNA, but their physical properties, for example melting point, vary. Physiological effects: mustard gas has extremely powerful vesicant effects on its victims. In addition, it is strongly mutagenic and carcinogenic, due to its alkylating properties. It is also lipopilic. Because people exposed to mustard gas rarely suffer immediate symptoms, and mustard-contaminated areas may appear completely normal, victims can unknowingly receive high dosages. Within 24 hours of exposure to mustard agent, victims experience intense itching and skin irritation, which gradually turns into large blisters filled with yellow fluid wherever the mustard agent contacted the skin. These are chemical burns and are very debilitating. Mustard gas vapor easily penetrates clothing fabrics such as wool or cotton, so it is not only the exposed skin of victims that gets burned. If the victim's eyes were exposed, then they become sore, starting with conjunctivitis, after which the eyelids swell, resulting in temporary blindness. Meiosis may also occur, which is probably the result from the cholinergic activity of mustard. At very high concentrations, if inhaled, mustard agent causes bleeding and blistering within the respiratory system, damaging mucous membranes and causing pulmonary edema. Depending on the level of contamination, Mustard gas burns can vary between first and second-degree burns, though they can also be every bit as severe, disfiguring and dangerous as third-degree burns. Severe mustard gas burns are often fatal, with death occurring after some days or even weeks have passed. Mild or moderate exposure to mustard agent is unlikely to kill, though victims require lengthy periods of medical treatment and convalescence before recovery is complete. The mutagenic and carcinogenic effects of mustard agent mean that victims who recover from mustard gas burns have an increased risk of developing cancer in later life. Skin damage can be reduced if povidone iodine in a base of glycopyrrole is rapidly applied, but since mustard agent initially has no symptoms, exposure is usually not recognized until skin irritation begins, at which point it is too late for countermeasures. The vesicant property of mustard gas can be neutralized by oxidation or chlorination, using household bleach, or by nucleophilic attack using for example decontamination solution DS2. After initial decontamination of the victim's wounds is complete, medical treatment is similar to that required by any conventional burn. The amount of pain and discomfort suffered by the victim is comparable as well. Mustard gas burns heal slowly, and, as with other types of burn, there is a risk of sepsis caused by pathogens such as Staphylococcus aureus and Pseudomonas aeruginosa. A British nurse treating soldiers with mustard gas burns during World War I commented, "They cannot be bandaged or touched. We cover them with a tent of propped-up sheets." Gas burns must be agonizing because usually the other cases do not complain, even with the worst wounds. But gas cases are invariably beyond endurance and they cannot help crying out. Formulations. In its history, various types and mixtures of sulfur mustard have been employed. These include, also known as HS or Levenstein mustard. This is named after the inventor of the quick but dirty Levenstein process for manufacture, reacting triethylene with sulfur monochloride under controlled conditions. Undistilled sulfur mustard contains 20–30% impurities, for which reason it does not store as well as HD. Also, as it decomposes, it increases in vapor pressure, making the munition it is contained in likely to split, especially along a seam, releasing the agent to the atmosphere. HDA, a code-named pyro by the British, and distilled mustard by the US. Distilled sulfur mustard sulfide. Approximately 96% pure. The term mustard gas usually refers to this variety of sulfur mustard. A much-used path of synthesis was based upon the reaction of thiodiglycol with hydrochloric acid. HTA, a code-named Runsol by the British, and mustard tea mixture by the US. A mixture of 60% sulfur mustard and 40% ethyl ether, a related vesicant with lower freezing point, lower volatility and similar vesicant characteristics. A blend of distilled mustard and Lewizit, originally intended for use in winter conditions due to its lower freezing point compared to the pure substances. The Lewizit component of HL was used as a form of antifreeze. HQA, a blend of distilled mustard and sesquimustard. Sulfur mustard agents. The complete list of effective sulfur mustard agents commonly stockpiled is as follows. History, development. Mustard gas was possibly developed as early as 1822 by Car copyright Zarmansua T.E. Despretz. Despretz described the reaction of sulfur dichloride and ethylene but never made mention of any irritating properties of the reaction product, which makes the claim doubtful. In 1854, another French chemist, Alfred Riche, repeated this procedure but he did not describe any adverse physiological properties. In 1860, the British scientist Frederick Guthrie synthesized and characterized the mustard gas compound, and he also noted its irritating properties, especially in tasting. In 1860, chemist Albert Niemann, known as a pioneer in cocaine chemistry, repeated the reaction, and recorded blister-forming properties. In 1886, Victor Mayer published a paper describing a synthesis that produced good yields. He combined 2-chloroethanol with aqueous potassium sulfide, and then treated the resulting thiodiglycol with phosphorus trichloride. The purity of this compound was much higher, and so were the adverse health effects on exposure much more severe. These symptoms presented themselves in his assistant, and in order to rule out the possibility that his assistant was suffering from a mental illness, Mayer had this compound tested on laboratory rabbits, most of which died. In 1913, the English chemist Hans Thacher Clarke replaced the phosphorus trichloride with hydrochloric acid in Mayer's formulation while working with Emil Fischer in Berlin. Clarke was hospitalized for 2 months for burns after one of his flasks broke. According to Mayer, Fischer's report on this accident to the German Chemical Society sent the German Empire on the road to chemical weapons. The German Empire during World War I relied on the Mayer-Clarke method with the 2-chloroethanol chemical structure already available from the German chemical dye industry of that time. Use. Mustard gas was first used effectively in World War I by the German Army against British and Canadian soldiers near Ypres, Belgium, in 1917 and later also against the French Second Army. The name Ypres comes from its usage by the German Army near the town of Ypres. The Allies did not use mustard gas until November 1917 at Cambrai, France, after the armies had captured a stockpile of German mustard gas shells. It took the British more than a year to develop their own mustard gas weapon, with production of the chemicals centered on Avonmouth docks. This was used first in September 1918 during the breaking of the Hindenburg Line. Mustard gas was dispersed as an aerosol in a mixture with other chemicals, giving it a yellow-brown color and a distinctive odor. Mustard gas has also been dispersed in such munitions as aerial bombs, land mines, mortar rounds, artillery shells, and rockets. Exposure to mustard gas was lethal in about 1% of cases. Its effectiveness was as an incapacitating agent. The early countermeasures against mustard gas were relatively ineffective, since a soldier wearing a gas mask was not protected against absorbing it through his skin and being blistered. Mustard gas is a persistent weapon that remains on the ground for days and weeks, and it continues to cause ill effects. If mustard gas contaminates a soldier's clothing and equipment, then the other soldiers that he comes into contact with are also poisoned. Towards the end of World War I, mustard gas was used in high concentrations as an area denial weapon that forced troops to abandon heavily contaminated areas. Since World War I, mustard gas has been used in several wars or other conflicts, usually against people who cannot retaliate in kind: United Kingdom against the Red Army in 1919, Spain and France against the Riffian resistance in Morocco during 1921-27, Italy and Libya during 1930, the Soviet Union in Xinjiang, Republic of China, during the Soviet invasion of Xinjiang against the 36th Division in 1934, and also in the Xinjiang War during 1936-37, Italy against Abyssinia from 1935 to 1940, the Japanese Empire against China during 1937-45, Egypt against North Yemen during 1963-67, Iraq against civilian Kurds and the Iranians during 1983-88 in the town of Halabja, possibly Sudan against insurgents in the Civil War, in 1995 and 1997, in 1943, during the Second World War, an American shipment of mustard gas exploded aboard a supply ship that was bombed during an air raid in the harbor of Bari, Italy. 83 of the 628 hospitalized victims who had been exposed to the mustard gas died. The deaths and incident were partially classified for many years. From 1943 to 1944, mustard gas experiments were performed on Australian service volunteers in tropical Queensland, Australia, by British Army and American experimenters, resulting in some severe injuries. One test site, the Brooke Islands National Park, was chosen to simulate Pacific Islands held by the Imperial Japanese Army. After WWII stockpiled mustard gas was dumped by the British in the sea near Port Elizabeth, South Africa, resulting in burn cases among trawler crews. The use of poison gases, including mustard gas, during warfare is known as chemical warfare, and this kind of warfare was prohibited by the Geneva Protocol of 1925, and also by the later Chemical Weapons Convention of 1993. The latter agreement also prohibits the development, production, stockpiling, and sale of such weapons. Development of the first chemotherapy drug, As early as 1919 it was known that mustard gas was a suppressor of hematopoiesis. In addition, autopsies performed on 75 soldiers who had died of mustard gas during World War I were done by researchers from the University of Pennsylvania who reported decreased counts of white blood cells. This led the American Office of Scientific Research and Development to finance the biology and chemistry departments at Yale University to conduct research on the use of chemical warfare during World War II. As a part of this effort, the group investigated nitrogen mustard as a therapy for Hodgkin's lymphoma and other types of lymphoma and leukemia, and this compound was tried out on its first human patient in December 1942. The results of this study were not published until 1946, when they were declassified. In a parallel track, after the air raid on Bari in December 1943, the doctors of the U.S. Army noted that white blood cell counts were reduced in their patients. Some years after World War II was over, the incident in Bari and the work of the Yale University group with nitrogen mustard converged, and this prompted a search for other similar chemical compounds. Due to its use in previous studies, the nitrogen mustard called HN2 became the first cancer chemotherapy drug, Mustin, to be used. Disposal: most of the sulfur mustard gas found in Nazi Germany after World War II was dumped into the Baltic Sea. Between 1966 and 2002, fishermen have found about 700 chemical weapons in the region of Bonham, most of which contain sulfur mustard. One of the more frequently dumped weapons was the Spra 1/4 bar 1/4 CHSE-37. These weapons contain sulfur mustard mixed with a thickener, which gives it a tar-like viscosity. When the content of the Spra 1/4 bar 1/4 37 comes in contact with water, only the sulfur mustard in the outer layers of the lumps of viscous mustard hydrolyzes, leaving behind amber-colored residues that still contain most of the active sulfur mustard. On mechanically breaking these lumps, for example, with the drag board of a fishing net or by the human hand, the enclosed sulfur mustard is still as active as it had been at the time the weapon was dumped. These lumps, when washed ashore, can be mistaken for amber, which can lead to severe health problems. Artillery shells containing sulfur mustard and other toxic ammunition from World War I can still be found in France and Belgium. These were formerly disposed of by explosion undersea, but since the current environmental regulations prohibit this, the French government is building an automated factory to dispose of the accumulation of chemical shells. In 1972, the U.S. Congress banned the practice of disposing of chemical weapons into the ocean by the United States. 64 million pounds of nerve and mustard agents had already been dumped into the ocean off the United States by the U.S. Army. According to a report created in 1998 by William Brankowitz, a deputy project manager in the U.S. Army Chemical Materials Agency, the Army created at least 26 chemical weapons dumping sites in the ocean offshore from at least 11 states on both the East Coast and the West Coast. In addition, due to poor record-keeping, about one-half of the sites have only their rough locations known. A significant portion of the stockpile of mustard agent in the United States was stored at the Edgewood area of Aberdeen Proving Ground in Maryland. Approximately 1,621 tons of mustard agent were stored in 1-ton containers on the base under heavy guard. An incineration plant built on the Proving Ground neutralized the last of this stockpile in February 2005. This stockpile had priority because of the potential for quick reduction of risk to the community. The nearest schools were fitted with overpressurization machinery to protect the students and faculty in the event of a catastrophic explosion and fire at the site. These projects, as well as planning, equipment, and training assistance, were provided to the surrounding community as a part of the Chemical Stockpile Emergency Preparedness Program, a joint program of the Army and the Federal Emergency Management Agency. Unexploded shells containing mustard agent and other chemical agents are still present in several test ranges in proximity to schools in the Edgewood area, but the smaller amounts of poison gas present considerably lower risks. These remnants are being detected and excavated systematically for disposal. The U.S. Army Chemical Materials Agency oversaw disposal of several other chemical weapons stockpiles located across the United States in compliance with international chemical weapons treaties. These include the complete incineration of the chemical weapons stockpiled in Alabama, Arkansas, Indiana, and Oregon. Earlier, this agency had also completed destruction of the chemical weapons stockpile located on Johnston Atoll located south of Hawaii in the Pacific Ocean. The largest mustard gas stockpile, of about 6,196 tons, was stored at the Deseret Chemical Depot in northern Utah. The incineration of this stockpile began in 2006. In May 2011, the last 1-ton tank of mustard gas was incinerated at the Deseret Chemical Depot, and the last mustard gas artillery shells at Deseret were incinerated in January 2012. The storage and incineration of mustard gas and other poison gases was carried out by the U.S. Army Chemical Materials Agency. Disposal projects at the 2 remaining American chemical weapons sites will be carried out at their sites near Richmond, Kentucky, and Pueblo, Colorado. In 2002, an archaeologist at the Presidio Trust Archaeology Lab in San Francisco was exposed to mustard gas, which had been dug up at the Presidio of San Francisco, a former military base. In 2008, many empty mustard gas aerial bombs were found in an excavation at the Marangaroo Army Base just west of Sydney, Australia. In 2009, a mining survey near Chinchilla, Queensland, uncovered 144 105mm howitzer shells, some containing mustard H, that had been buried by the U.S. Army during World War II. In 2010, a clamming boat pulled up some old artillery shells of World War I from the Atlantic Ocean south of Long Island, New York. Multiple fishermen suffered from skin blistering and respiratory irritation severe enough to require their hospitalization. A large British stockpile of old mustard gas that had been made and stored at MS Factory, Valley near Hydyman in Flintshire, Wales, since World War I was destroyed in 1958. In 2014, a collection of 200 bombs were found on the boundary between the Flemish villages of Parsendale and Meerslade. The majority of the bombs were filled with mustard gas. The bombs are a leftover from the German army and were meant to be used in the Battle of Parsendale in World War I. It was the largest collection of chemical weapons ever found in Belgium. Detection in biological fluids, urinary concentrations of the thiodiglycol hydrolysis products of sulfur mustard have been used to confirm a diagnosis of chemical poisoning in hospitalized victims. The presence in urine of 1,1-sulfonylbismethylthioethane, a conjugation product with glutathione, is considered a more specific marker, since this metabolite is not found in specimens from unexposed persons. Intact sulfur mustard was detected in post-mortem fluids and tissues of a man who died 1 week post-exposure. See also. References. External links. Textbook of Military Medicine. A Euro-intensive overview of mustard gas includes many references to scientific literature, detailed information on physical effects and suggested treatments. II Rebos Y. A recent exposure to mustard gas in the United States, clinical findings of a cohort 6 years after exposure. MED-Gen MED6, 4. PMCA 1,480,580. PMIDA 15,775,831. Shows photographs taken in 1996 showing people with mustard gas burns. An overview of the sulfur and nitrogen mustard agents, questions and answers for mustard gas, UMDNJ Rutgers University Counteract Research Center of Excellence. A research center studying sulfur mustard, includes searchable reference library with many early references on sulfur mustard. Treatment of mustard gas burns. A Euro published in the BMJ in 1946, Nightmare in Bari, Surgical Treatment of Sulfur Mustard Burns, UK Ministry of Defence Report on Disposal of Weapons at Sea and Incidents Arising, Hydyman Valley History Society, The Advent of Mustard Gas in 1917, Simon Jones, Measures to Protect Against Mustard Gas, 1917 to 1918, Simon Jones.